So instead of waiting for everyone to join at 7:10, I'll begin 1 or 2 more minutes. I'll begin slow and I won't jump straight away into using Simscale. I'll just give a brief introduction first, and that will give enough time for the rest of the students to join. Okay, then and I must be audible by now, and I hope you're seeing my screen and my mouse pointer as well. So thank you all for joining this session. I know it's after hours, but uh, participation would be quite useful, especially for the third years in the design project and the final years for their final year projects if they have some mechanical component within it. And the use is not limited to that, of course. Once you go into the industry, you come across instances where you need to do some finite element analysis based simulations, regardless of what industry that you're in. I personally have come across such situations, and apart from the regular duties that I have done, and in such cases, I have used Simscale to provide the answers required by my seniors and other managers and so on. Well, there are, before we jump in, you may see that the name of the software is, of course, Simscale. And a brief explanation of what Simscale is that it's generally a cloud based finite any element analysis solver or a finite volume method solver. So FEA is used for mainly mechanics related simulations, and FEM is used for fluid dynamics based simulations, or CFD for short. Today we'll look at mechanics simulations related to structural mechanics and so on. Based on the feedback, and whether if you want me to do any other sessions in fluid domain as well, we can do how we can have a session on how to use Simscale in, for CFD as well in another week. Right. So I have prepared a few slides, just four of them, before we go into modeling on Simscale. Just to give you a brief idea on what Simscale is and where it's supposed to be used, and how it's different from the mechatronic system modeling software that we have been used for the fourth years, which is Simulink and Simscape. So one of you asked this question specifically this morning, and that's why I have prepared these few slides. I thought it might be important to you to figure out, to be able to figure out where Simscale is used and where these other Simulink and Simscape softwares are used. And despite the quite similarity with regards to the name, these softwares are provided by two separate providers. And Simscale is basically a cloud-based software, and Simulink Simscape is provided by the MathWorks. And they do have a cloud-based version of their own, but As you know, it's limited to 20 hours per month. And it's quite lagging, and uh, we use it installed on our PCs. Now, enough of that. Uh, Both Simscale, Simlink, and Simscape, all these softwares are used for some sort of modeling and modeling of mechanical and mechatronic systems. Although Simscale is mostly in the mechanical domain, and only a very small amount of mechatronics systems can be simulated in Simscale. With regards to the mathematics that goes on behind the curtains, Simscale depends on the finite element method and finite volume method. I won't go into detail with regards to what this is. You can look them up online and watch some videos on YouTube to figure out what they mean. And on the other hand, Simulink and Simscape based softwares, they typically use the approach of developing transfer functions so that they can predict what the output is for a given input. That's what goes on behind the curtains behind each of these software. And the second most significant differentiating factor between those two is how they represent what they are modeling. Now, we spoke that we use all these software to model mechatronics or mechanical systems, and we cannot. The most important fact when it comes to modeling mechanical systems is the geometry and its associated properties, such as density and mass distribution, and so on. In SimScale, a body is modeled as a geometry which is built up of a large number of small geometries. It might not be clear to you with what I meant using this sentence. I'll show you later on uh, in the software itself. Then you'll be able to visualize what's really going on. Just know that SimScale breaks down a geometry into a large number of, perhaps millions of smaller geometries. In the case of Simulink and Simscape, a body is represented as a single coordinate frame and a matrix containing the holistic information, which means that you will have a single coordinate frame, which is an origin plus three principal axes, which track the position and the orientation of the body. And this matrix containing holistic information means it will keep and it will hold multiple variables which track what the whole mass is, what the whole density is, but it won't hold any details with regards to the exact distribution of mass. The difference will be clear to you as you move on into the software. And finally, the third most important differentiating factor with regards to these two is that if we apply a simple equation to a body in SimScale, SimScale will in effect apply this equation to all the constituent smaller bodies within it. So if somebody, let's say a quadcopter frame or something, is what we are studying, this quadcopter frame in SimScale will be broken down into millions of smaller geometries, mostly prisms and pyramids. And when we apply F equals ma to that quadcopter frame, SimScale will in effect apply the equation to each and every one of those millions of prisms and pyramids which make up the body. But in Simulink and Simscape based systems, if we apply F equals ma for a quadcopter body, then that means only that equation will be added to that point mass, which is modeled using the coordinate frame and the matrix. Well, to make things clearer for you, I have added an example and we'll discuss it in the next few slides. We'll jump straight into the exam. Okay, let's take a case which occurs in real life and figure out where to use SimScale and where to use Simulink and Simscape. The case I am studying is a ball being hit by a bat, perhaps a tennis ball or a cricket ball or something. You just throw it in there and hit it by a bat. That's the case that we'll be studying. What we can study with SimScale, now this word can is really important. What we can study in SimScale is the deformation the ball undergoes when it comes into contact with the bat. I don't know whether you have seen it or not. In the case of tennis balls, it's quite visible if you observe it closely. But when a ball is being hit by a bat, in order for the energy within the bat to be transformed to the ball has to be deformed by some amount, and then only will the ball gain that energy and the velocity in the process. SimScale can be used to study the deformation the ball undergoes and to an extreme amount of detail, and that cannot be done using Simulink and Simscape. That cannot. And in addition to this deformation, so this deformation will be an FEA simulation, or what I would call a structural mechanics study. This is an FEA or structural mechanics study. So after that study, we can also study the air resistance of the ball with respect to its motion within air. So that will be a CFD or a computational fluid dynamics study. And let's not discuss in detail what really is, but just know that it can be studied within SimScale. And it cannot be studied in Simulink and Simscape in detail. But what people really do is, with regards to air resistance on the ball, they first study the air resistance using sim software like SimScale. Then they come up with equations which kind of simplify the effects of air resistance on the ball. And those equations are used within a Simulink and Simscape environment to study the trajectory of the ball after being hit. And these FEA and CFD solvers, they really do not study things like the trajectory of the ball. Things like that are dealt with uh, systems modeling software like Simulink and Simscape. Well, I think this is quite a sufficient example for you to figure out where do you SimScale and where do you the Simscape environment. Sorry, where do you SimScale and where do you the Simscape environments. And if you still have doubts with regards to what software you use for which application or which study you're going to conduct, as you should since you are still in the learning phase, then you can ask generative AIs or regard to ask generative AIs to obtain an idea of what to use. I have seen that they typically point you towards the right answer. However, I don't know whether it's an appropriate approach to take, but that's one that you could take. And in addition to that, you could ask advice from the lecturers within the department of what to use. And in addition to that as well, what I would really do and what I really have done in my undergrad days was, if I was studying a certain application, I would, since in most cases I am not the one who is studying this for the first time, I would go over to Google Scholar and figure out what other people have done and what softwares other people have used to study this particular application, and then when you do this for quite some time, you will with time develop a sense on which software to use for which applications and figure out the limitations of each. Well, that brings an end to the intro of Simscale. And I think it's time for us to move on to discussing how we use it for an actual study. So let me check. Okay, so I have Simscale open in my web browser, but before I oh, okay, so just let me go in to the Simscale homepage and we'll come back to the slides to figure out the steps. So as I told you in the first slide, it's a cloud-based software, which means it runs on Simscale servers somewhere, perhaps in the USA, and we access it through our browser. At the moment, all competitive softwares which do FEA, such as ANSYS, Abacus, SolidWorks simulation, and any other FEA software that you may know, they run on the desktops, on your own desktops and in-house supercomputers in some universities. And they also provide, in the case of ANSYS, you are an option to run it on AWS and access it through a web browser. All even cases like that where you run it on AWS is locked behind a paywall. And currently, Simscale is the only provider which gives us access to cloud-based FEA software for no cost. And when I say no cost, you really don't even need to give credit card information to sign up to use Simscale. And it's not some hobby software. It's used as leading academic institutions and leading corporate entities for real work. But they do pay for what they are doing. But in our cases, they provide us 3,000 core hours per year and 10 successful simulation runs with the numerical results per year. And believe me, that's sufficient for all our undergraduate engineering requirements. So, as an undergrad, and perhaps even as a practicing engineer or a postgrad, this is a definite software which needs to be in your arsenal, software arsenal. And again, you can check out the pricing and the limitations under this tab. Well, you'll never exhaust these 3,000 core hours. Despite all that I have done, I have never exceeded this. But we didn't have this 10 unrestricted simulation restriction within my undergrad days. It's there now. So what I propose you to do is have two accounts for two email addresses and use one account to do trial simulations. And after you do 10 successful simulations, you'd still be able to do further simulations, but you won't be able to obtain numerical results. So keep one email account for trial simulations, then you can do tinkering with the simulation parameters. And once you kind of feel that you have converged to the proper simulation parameters, then you can run the actual simulation on the account you have reserved for the actual simulations. That's kind of how you would circumvent the restrictions that they have uh, kept for the time being. Perhaps they will include more restrictions in the future. I don't know. But having multiple accounts linked to multiple email addresses is what you can do. Right. Well, that's regards to the pricing. And The fourth years who have been in my mechatronic system modeling uh, class know that I emphasize a large amount on reading online documentations when we were taught when we studied MathWorks suite software. And in the case of SimScale, that would be the case as well. I would encourage you to read the case studies, tutorials, and documentation of the SimScale platform if you are going to master this software. That all being said, let's finally jump in on how to use the software. Okay, so what I am demonstrating you is actually a tutorial which I got from the tutorial library available for SimScale. It will be a static structural simulation, and this is the screen that pops up upon me opening the tutorial. So I have just opened the tutorial and I have done nothing else. And I'll guide you with regards to the IDE and the steps you have to take to run a successful simulation. Now, some of you may have already done ANSYS or at least SolidWorks simulation to do some static structural studies. And you may notice that compared to those two software, this is quite decluttered and extremely user friendly. On the on the lower right corner, you see a triad which you can use to figure out what the current orientation is, and this is quite important. You have to pay attention to this triad, especially in cases when you are specifying the gravitational fields and the directions the forces are applied on any body that you have. So I'll go through the rest of the IDE as we progress through the simulation. Up at the top, I'll describe this as we progress in the simulation as well. Before I do anything else, especially in the case of FEA and CFDs, and this is true with regards to any simulation study, knowing what you are studying and knowing your objectives and knowing what results you are looking for before you before you set any parameters of the simulation is quite important. In this case, this is a connecting rod in an engine. So my objective is to study the deformations which take place within this body and the displacement which undergo uh, displacement each point undergoes as effect of that deformation when a force is applied inside this bearing mount in the negative y direction or in the downward direction. So let me re-explain that. I have this connecting rod. If I keep this face fixed, which is colored in red now, if I keep this face fixed and I applied a load on this internal cylindrical face in the downward direction, uh, this crank rod will undergo some deformation. If you rely on your basics mechanics of materials knowledge, you should be able to kind of intuitively figure out that this area will undergo some extension and this area will undergo some compression. And as a result of that, uh, points at the extreme ends will undergo a large displacement. Now that's a uh, explanation of what might happen when I keep certain phases fixed and keep apply certain forces to certain phases. But we what we require from the FEA study is to quantify that, to obtain quantities for what we qualitatively described. Well, that's our objective for this study, and that's what we are looking at. Okay, so when I saw this tutorial already comes with a geometry already imported, but in a later tutorial, I'll show you how to import CAD files into Simscale as well. So don't worry about that. I'll show it in half an hour or so about how to import CAD models. But let's just begin with what's already offered in the tutorial. So after importing the CAD model, we have in the IDE will direct us in a user-friendly manner towards what we have to do next. And this is what it has directed me to do. That is to create a simulation. So let me click it. And upon clicking on create simulation, now I'm required to select what kind of simulation that I need to run. So it's basically divided into two categories, flow and structural. Flow deals with the CFD aspects of the CFD simulations, and as the name implies, it's related to fluid flow. And under the structural category, you have multiple simulation types which deal with multiple subcategories within structure. If you click on each of these subcategories, it kinds of give you an explanation of what they can do. I've clicked on static, and under static, the brief description is that you can use it to determine displacement, stresses, and strains in structures caused by loads. So that's kind of what we need to study over here. We are applying a load. We are keeping one phase fixed. When we need to quantify what the displacements and the stresses within this crank rod might be. So one simple reading of the description, we kind of see that this would be sufficient for us. But we can also go into the descriptions of the other available subcategories and see whether they offer any other additional features or not. Go into dynamic. In dynamic, they usually depend on time-dependent calculations. And in my problem definition, I didn't really touch on whether it was time-dependent or not. So that must mean we don't need dynamic analysis at the moment. I didn't say anything about heat transfer as well. That's a rule of thermomechanical as well. And you'll see that the descriptions for harmonic and frequency analysis uh, is not what we really require. So based on my problem definition and the description for the subcategory, I think it's quite clear to you now that what the subcategory that we'll be needing is static analysis under structure. So after selecting that, I just need to create or end the creation of simulation and proceed to the next stage. Now I have gone to the next stage. And, that falls into the second step in the FEA study where we describe boundary conditions and so on. But forget the slides and let's focus on what the IDE of the software guides us to do. If you are still in the learning phase, what I recommend you to do is study the simulation parameters one row at a time and complete all the parameters until you don't see any of these red circles and see only green ticks in front of all of these parameters. A green tick means that, let's take for an example the parameter contacts. If I have the green tick in front of the parameter contacts, it means that uh, I can run a successful simulation based on what I have currently specified for these parameter contacts. So we'll go through each of these parameters one by one and figure out what we need to do based on what our objective is. So the geometry has already been important. That was handled by the tutorial. Now contacts parameter and its kind of brother parameter, the connectors parameter, they are used when you have more than one body in the simulation. You may have heard of multi-body paths, which means a part is built out of multiple bodies connected together in some manner. Let's say, for example, welded joints. If you have such a body, then you need to specify what those contacts are. If you have welded joints, then perhaps you would be using bonded contacts. So this is not a multi-body part, and since this is our first tutorial, I chose an extremely simple one. This is just a single body part, and therefore we won't have to specify any contacts or connectors for single body ones. That's why the green tick is in front of these two parameters. So it's safe to say that we can proceed to the next. Well, we have another parameter called element technology. And so it's related to the process called meshing. And meshing is where we break down this whole single body into millions of constituent bodies. At the moment, I suggest that you keep everything at its default settings for with regards to element technology. If you don't mess around with it, then that's fine. Keep it at what the default values. Keep it at its default values. Then you'd be good to go. For most of the cases, you will encounter in your undergrad and yes, undergrad studies. And if you ever need a case where you need to change how the meshing is done, uh, you'll know what to do upon reading a paper of a study, a similar study once done by some other person. If you read such a paper, then you will notice that uh, they usually describe what the mechanical mesh orders and what reduced integration parameters they use are. But at the moment, we'll keep it at the default values since your undergrads will not go into detail about that. Now, with regards to model, what we have to specify under model depends on the study that we are conducting. So this is a static structural study, and in the static structural study, we only have to specify the direction of gravity. Perhaps had it been a thermomechanical or harmonic study, we might have had to specify more parameters under model. But for static, this is we only had to specify gravity. And you don't need to keep in mind what you have to specify for each and every type of simulation. The software keeps track of it for you, and once you select the type of simulation, then it will only ask the parameters which need to be specified from you. So that's kind of a user-friendly feature in Simscale. Because if you have used other software like ANSYS, then for model you might have a whole tab and a whole bunch of buttons and menus where you need to keep track of what you need to specify for the type of study that you are taking and specify a whole bunch of things. But in Simscale, the software handles that for you and only ask the necessary questions from you. So someone has to keep the mic switched off, right? So we need to specify the gravity. The gravity specification can be done by specifying its magnitude of its gravitational acceleration and the direction of the gravity with regards to with respect to the triad, the orientation triad that's given over here. So you can specify the gravitational acceleration. It's a constant. It's 10. If you are real stickler, you can use 9.82. And with respect to the direction, at the moment for this study, gravity doesn't really matter since this effect is not the deformation effect isn't caused by gravity, but the significantly larger forces that is applied to this internal cylindrical surface. So gravity is quite insignificant in this study, but however, I'll still apply gravity just to show you how gravity can be applied. So since it's significant for this study, it doesn't really matter with regards to what direction I apply gravity in. But let's say I applied it in the negative y direction, and if I want to do that, I just specify the vector component of Ey as -1. If I want to apply the gravity in the positive y direction or the upward direction when I look at it from this orientation, I would be specifying it as 1, and based on whatever your requirement is, whatever direction you want gravity to be applied in, consider this as a direction vector and make the appropriate components. Okay, so I have applied it in negative y. That's it for the gravity. And since gravity is the only thing that we have to specify on the model, once that I have this specified, a green tick will appear in front of model as well. So now we have gone through 4 parameters and we have really done nothing significant yet. The first significant thing parameter we specify will come under materials, where we specify materials for any number of bodies that we might have. So this is not a multi-body part, just a single body, just this crank. And so upon clicking this plus sign, it will give me a list of materials, a very short list I might add. And I just need to select the material which is closest, then apply it. I'll use steel and apply it. And upon clicking apply, that material steel will be applied to the whole body. Now I want to emphasize that this material list is extremely incomprehensive and extremely short. It doesn't even come close to providing models for the all materials that we have. But you can create custom materials, and I'll show you how that can be done. So let's say, for example, if you consider steel, there are around hundreds of variants of steel available. I call it 10, 30, 10, 40, or whatever it is. And AIs has also have mild steel, plain carbon steel, stainless steel, and so on. Let's see how we specify what we want, how we specify a subvariant of steel. So at the moment, I have clicked steel and applied it. And that will bring up a pop-up menu which allows me to specify the Young's modulus, Poisson's ratio, density, and whether the directional dependency is isotropic or orthotropic. So if you want to specify a subvariant of steel, then you can look up that subvariant, let's say stainless steel AISI 304. You can Google uh, for the properties of ASI 304. Find out what the Young's modulus, Poisson ratios, and densities for that particular material, and just change the parameters over here. And after doing that, you can change the name as well. That's how you circumvent the fact that the list of material is quite it's a material being incomprehensible. Well, if you have used ANSYS, you will see that even applying a simple material in ANSYS is quite a hassle with large amount of parameters to be concerned with. But in Simscale, it has been quite simplified, and some compromises have been made. But for undergrad cases, it's and in most industrial cases as well, this is quite useful, since in the industry you won't be using very cutting edge materials which have been discovered a few days ago. You'll be using tried and tested material which is widely available. And for such materials, these Young's modulus, these parameters will be published and freely available on the net. So that's not really a compromise, but uh, researchers will feel the difference. But between the advanced functionality provided by ANSYS and quite of the limited functionality provided in SimScale, but for our purposes, that's extremely fine. So let's finish specifying the material steel, and let's move on to boundary conditions. Now, this is kind of the hardest part, and even in a simple simulation like uh, this would this won't be hard, but you have to you have to pay extreme attention to what you are doing with regards to setting the boundary conditions. The reason is that you can set up boundary conditions in a manner which is not appropriate and still run a successful simulation, but you'll be modeling some other scenario instead of the scenario which you are actually supposed to be studying. And that's the real danger over here. And there are no safeguards provided by SimScale, and even in ANSYS, they don't provide any safeguards to prevent us from modeling a scenario which isn't what we really want to study. So setting up the boundary conditions in the appropriate manner is a skill you need to gain through practice and through reading papers of what others have done. So in my undergrad days, how we mastered boundary condition is we had a module where we were supposed to look up mm, papers of CFD studies that other people have done and set up boundary conditions, and write a report on not write report but set up ANSYS simulations on appropriate boundary conditions based on what they were studying and what they have done. So the message I need to convey to you is that setting up boundary condition is a skill that you'll gain through observing what other people have done, and what other people have done is documented in scientific papers. Okay, well, that being said, let's focus on how to set up the boundary conditions for this small application. And let's recall my problem definition. My problem definition was to fix this the internal surface of the larger cylinder. I fix these faces that I have selected in red, and to apply a force on the internal cylindrical surface of the smaller cylinder and figure out what the displacements and the deformations were. So from the problem definition alone, for this case only, I'll be able to figure out what the boundary conditions need to be. Some boundaries will need to be fixed, and on the other boundaries, a force will need to be applied. Now let's see whether the boundary condition options that's given by Simscale, whether some of these can be fixed and a force be applied on the other surfaces. I'll click on this plus sign, and out will pop a list of boundary conditions which I can apply on the boundary of my choice. Start with bolt preload through force, pressure, fixed supports, and cylindrical hinges, and so on. Once again, I'll bring up the fact that nothing is going to prevent you from specifying the boundary conditions in an inappropriate manner and simulating some other scenario which is not actually the objective of our study. So we, in our case, we need to keep some boundaries fixed and a force applied to the others. In the case of the fixed boundaries, I'll be specifying it through a fixed support boundary. You can go over the list and see that in this list there's no other boundary condition which enables me to fix surfaces. The word fixed is within this fixed value boundary condition, but fixed value is not really used to fix faces. And to fix faces, fixed support is the boundary condition that's used. If you want to really figure out what's the difference between these two, that can be done by going to the documentation and reading through uh, what each and every one of these boundary conditions are used for. Okay, so we'll select the fixed support, and under that we can select the facets which need to be fixed. And if I zoom closer to the symbol which appears over here, you will see that this is quite similar to symbols you'll see in engineering drawings which specify a fixed face. So if I were to draw it, it's actually a symbol like this, in case that you can see the lines over here. So in engineering drawings, this is kind of the symbol that we use to imply that that particular face is fixed or not. So give me a moment, I need to, so give me 5 minutes. I need to go over and right. Sorry for the interruption, and let's begin where we left off. So I selected the fixed support boundary condition, and I selected the faces on the assigned conditions pop-up menu, and we discussed the symbols and similarity between what we see in engineering drawings with regards to bound certain faces being fixed. and I click on the tick and save the boundary conditions, and you will see that at the moment everything on top of the mesh parameter has a green tick in front of it, which means we should be able to run a successful simulation just by doing the meshing and running and adding a simulation run. So that's what I meant when I said that there are no safeguards provided by Simscale which allow you to prevent running modeling a scenario which isn't what you really want to study. So be careful of that. So even though you have green ticks over here, specifying all the boundary condition is not yet done. You have to keep the problem definition in mind when you're specifying boundary conditions to check whether you have properly specified all the required boundary conditions. So let's recall our problem definition once again. We kept a certain set of phases fixed. We applied a load to another set of phases, and then we want to find out the deformations and the displacements. We specified the fixed phases, and now we want to specify what phases force should be applied to. So let's add a boundary condition, and it's quite evident that we'll be using the force boundary condition. I have selected it. First, I'll select the phases which it will be applied to, and I'm applying the force in a downward direction when viewed from this perspective. I'll be applying it on the internal faces of this cylinder. So definitely I'll have to select these two faces. Now with regards to these two, I can still select them and the simulation would run just fine. But I choose not to do so because in real life, when a force is, if there's a pin or shaft going through this internal cylinder, sorry, internal hole, if that shaft is applying a force on this internal hole, these two surfaces won't really come into contact with the shaft, and the contact will mostly happen through the bottom surfaces. I chose not to select these two faces, but even if you do, you won't see a large error to that. So if you select these two faces, that would be fine, but there'll exist at least somewhat a small error, since in real life there won't, even though it's invisible to the naked eye, these faces won't come into contact when that pin is pushing downwards on the crank. Well, now we have selected the faces and we need to specify the direction of the force and its magnitude. So our force will be in the downward direction when viewed from this perspective, and that would mean it would be in the negative y direction. And let's say I am applying a force of 200 newtons or so. I need to specify the force components in the principal axis directions. I have no components in the x and z directions. It will be completely a force in the y direction and it's negative y. So I'm specifying negative 200 under fy and setting it to save. Now once again, you have to go through your problem definition in your head and figure out whether you have applied all the necessary boundary conditions. As a practice, I do this every time I add or remove a boundary condition, since this particular area is where you're most prone to make a mistake. Right. So let's go to definition once again. We are keeping a certain set of faces fixed, applying a force on another set of faces, and we need to find the deformation and the displacements which of the areas within this body. We have specified the fixed faces and the forces the force is applied to, but with regards to the deformations and the displacements, it's not really something we specify, it's something we calculate through the simulation. So it's not a boundary condition. I hope that is clear why deformation and displacements are not a boundary condition, but something we need to find at the end of the simulation. Those two parameters are what we uh, will obtain at the end of the simulation. So I have gone through the problem definition once again and affirmed that I have specified all the necessary boundary conditions, and therefore I can proceed to the next stage, and that would be specifying the solver settings. Now, if I were to go through all the sub parameters of solver settings, then I would need a whole other session or perhaps a few other sessions just to focus on how to specify solver settings. So it's quite intricate, and Simscale has provided us with a default solver settings, and I suggest that you use it. For most of the primitive cases, this would be fine, and but even when you move into a moderately complex case, you will need to look up the documentation and find which of these solver settings are most suitable. If the final year students remember that even in MathWorks, we set the solver settings to auto, which is quite different from keeping it at the default settings. If you set it to auto in MathWorks or Simulink and Simscape software, that software will figure out what the best solver setting is for the model that we have developed and run the solver at its optimal settings. That's extremely different from what we do here. Here we just keep it at the default values, and when we keep it at the default values, the solver does not figure out what's best. It just follows a set of solver settings in a blind manner. Simscale does not currently have that facility to figure out the optimal solver settings. So what we can do is, so we'll have to do it manually when we venture into a moderately complex model and have to specify the intricate details of the solver. And in that case, you'll need some advanced knowledge with regards to FEA. And for that, papers and documentation won't be sufficient. You will have to look up uh, textbooks on FEA and follow the guidelines as well with regards to figuring out the best numeric settings. But 75%, I don't know whether it's proper to give a number like that, but a majority of undergrad projects can be done by sticking to the default numeric solver settings which are provided. Perhaps your simulation settings would take longer to be achieved, but that's a sacrifice uh, which is advisable to be made, since otherwise you'd have to spend months, months going through textbooks to figure out what's best. So my suggestion for you is, especially with regards to undergrad projects, to keep these numeric settings at its default values and go to the next stage. With regards to simulation control, You don't need to concern yourself with regard with the time stepping parameters since we are running a static simulation. But if you run a dynamic simulation, then you'll need to specify for how long the simulation needs to run and what the step size needs to be. And this also doesn't need to be specified under this kind of study. The maximum number of processes cannot be determined by us using the community edition. So there's in the end for this kind of study, there's nothing to be specified under simulation control. Keep them at its default values. But these are kind of things that you can uh, you will definitely have to specify if you're going into at least a moderately complex simulation, which this is not. So we'll take a look at these results controlled parameters perhaps in a later week if you are interested. But these aren't things that you cannot ignore. You have to pay careful attention to these things when you're doing at least a moderately complex simulation. But today is not the day for study results control. We'll keep them at their default values as well. Now, finally, so we have gone through defining geometry simply by importing a CAD model. Then we have defined the boundary conditions, which was the area which was most prone to errors. Then we come to a step called meshing. Now, meshing is what breaks down this single body part into a large amount of constituent elements. And after I generate the mesh and visualize it, then it would be clear with regards to what it does. So let me simply run the meshing process. They estimate that it will take around 0 to 7 minutes for it to happen. So I'll run it, and after the meshing is complete, then we'll be able to figure out what has gone within the process. Now there are a few parameters that you can specify over here as well. This is also something that you can't leave at the default values if you're going into a moderately or for even simple simulations. Don't leave the mesh settings at its default values. You need to specify mesh settings manually and add some refinements as well. But since this is our first day, we'll keep it at its default values, but it's not recommended to do so. Uh, there are textbooks that you can follow, give you some rules of thumbs on how to set up mesh settings properly. And even scientific papers will also have some guidelines with regards to what mesh settings other people have used for their particular studies. So I'll just generate it. It will take some time. It's estimated that it would take around 7 minutes. So we'll have to wait for some time. And during that time, you can come up with questions that you may have had while I went through or rushed through setting up the solver settings. So if you have any question, now's the time to bring them up because once the meshing ends, I'll jump straight in to do the simulation. So no questions. Right. So I'll take it as you are extremely familiar. Like, perhaps you guys have already familiar with Simscale, or I managed to convey what I wanted to convey. and you have no questions because of that, because this is not a place to be shy. You don't need to worry about asking the wrong questions. There are no such thing as wrong questions when it comes to engineering, and especially when it comes to learning engineering. But since the machine has finished and I need to move into simulation in a quick manner, you will have another time window to ask your questions once I begin simulation. So if you do have them, ask questions then. I'll go through what meshing has done. So initially we had a single body, and now the meshing process has deconstructed our body into 16,000 smaller cells. So these cells are prismatic and tetrahedral. If you study their geometry, by tetrahedral, I mean it has four faces, all of which are triangles. And some of them might be prisms, where one face is not a triangle but a square. So if your meshing process has been done appropriately, then a large amount of those cells should be tetrahedral. The more tetrahedral your mesh is, the better your mesh quality is, and subsequently, the better your simulation or the more accurate your simulation results would be. This can be studied under mesh quality parameters, but I'm not going to do that now. If you go into mesh quality, then you'll be able to bring up reports on whether your elements or cells within the mesh are tetrahedral, prismatic, or not. Now you'll see that there are smaller cells closer to the boundaries or closer to sharp changes in geometries. And in places where there aren't really any sharp changes in geometry, the cells are quite big. We didn't go into mesh refinements today, but if we had gone into refinements, you would have been able to specify limits on the size of cells at particular areas. A rule of thumb with regards to mesh refinements is that in areas where there are sudden or more drastic changes in the geometry, you would have to use more refined or extremely relatively smaller cells in such areas, and also closer to the boundaries the mesh size has to be smaller. So you'll come across more rules of thumb like that if you were to read textbooks with regards to FEA. That's up to you if you want to do it or not. Now that I have a mesh, I'll change one parameter called fineness, and I'll show you what the difference in results would be for you to be able to visualize that in a simple manner. I'll take a screenshot of it, hold it for later memory. So I have increased the fineness up to 10. Now, on doing that, they estimate that the number of cells will go up to 50,000. So remember, based on the current machine that we have done with the coarseness, with a fineness of 5, we had 16,000 or so cells. And if I increase the fineness, the number of cells would go up. I'll regenerate the mesh again to show you what the difference in results would be. And this time it would take more time than before, since the process would now be breaking it down into more constituent elements, and that would take up more time. So once again, you have another window to ask questions, which I hope that you have. So I think most of the participants are from year three, of third years. I don't see many fourth years names I am familiar with over here, but that's fine. We'll be making the video available. It's still recording. Right. This. Well, it has resulted in 35,000 cells. And now I'll bring up the previous mesh that we had side by side. Pay closer attention to this area over here, and you'll see that the cells are much smaller now, especially in the areas where there's a extreme sharp change in geometry. Just this area. So a change in the fineness parameter, you can it's kind of a general metric on how small your elements would be. If you want to make elements smaller in a particular area, then you'd have to use mesh refinements, but we won't go into that today. And I'll proceed to running a simulation. Now, at this moment, I have specified model parameters, boundary conditions. I have done the meshing, and I can start a simulation. And to do that, I just need to click on this add button, specify some name, and start it, and it will begin doing the simulation. And what it means by doing a simulation is that after meshing, it has now been deconstructed into 35,000 cells. And the equations like F equals MA and the stress by strain relationships would now be added, now be applied on each and every one of these 35,000 cells. And the solver will come up with at least 35,000 simultaneous linear algebraic equations, and then it will move on to solving those equations. I think it's improper to say that it comes up with at least 35,000, but it would be more accurate to say that it comes up with a multiple of 35,000 equations. But you don't need to concern yourself with regards to how many equations are being developed. It's handled for you by the solver. So that was something unnecessary that I brought up. But if you pick up a textbook on FEA and read through the introductions of each and every chapter, then you'll gain quite a good understanding with regards to what goes on behind the curtains. Just skip the math parts and read the intro pages in each and every one of those chapters, then that would be enough. That would be sufficient for you to gain an intuitive understanding without knowing what the math is. So now the simulation has completed. That means the solver has finished solving this set of linear algebraic equations and has obtained a result. And what's left for us to do is to visualize the result. That's called post processing in the field of FEA. Visualizing is just the layman's term. The scientific or the proper term is post processing the results. Now we can obtain visualizations for the results, but they will be available as a CSV or Excel file as well. But we gain an intuitive understanding when we visualize the results. And so at the moment, I am plotting something called von Mises stress. I'll come back to what it is later on. But before we, all right, let's just go over through what these are. Then finally, we'll come to an animation and you'll be able to figure out what happens. So let's plot x displacement. That means displacement along the horizontal direction. We'll keep the units at millimeters. The maximum x displacement is in the micrometer range. That means it's quite insignificant. Let's take a look at y. Once again, insignificant. For z as well. Right. So with regards to 3 axis, there's quite a significant relative deformation in the z direction. So was it x? Right. As should it should be the case. Uh, the displacement along the x-axis is the most significant, and the largest x displacement happens at this place, at this location, as it should be the case since when a force is applied on these surfaces in the downward direction, won't go down but rotate around the fixed faces and thereby result in a combination of y, x, and z displacements. This will be quite clear when you go into the animation. However, uh, that's how you interpret results using a plot like this. Right. So now I have brought, previously we studied displacement, now we study strain. And the strain plot can be used to figure out where extension takes place and where compression takes place. If you have some strain which is positive, then that means an extension. And if you have a strain which is negative, then that means a compression. As it should be the case, the upper side of the crank undergoes extension and the lower side undergoes compression. And we would have been able to figure out what happens using qualitative analysis of the physics using without doing any mathematics. But that since we have done the study, now we have, in addition to the into confirming the intuitive prediction, we also have a numerical value for what the strain and displacements are. Now, what's most important is the von Mises stress. I'll use the units megapascals. And this is the result parameter used to figure out whether the crank will undergo some failure when this particular force is applied. Well, you know, the stresses that we obtain are in along three principal axes, and the von Mises stress is kind of the 3D resultant stress of the stresses along three principal axes. In the case of steels and most metals, if the von Mises stress at some point are above the yield stress for that material, that means at that point yielding will take place. And in all types of material, if the von Mises stress is greater than the UTS or the ultimate tensile stress, uh, then failure will occur at that point. So keep in mind, this is the parameter that we use to figure out whether mechanical failure will occur or not. For steel, yield strength is for for all steels, yield strength is above at least 300 megapascals or so. So at a one meter stress of 22 megapascals, no failure would happen. But let's go to the animation, and through running an animation, you'll be able to figure out or able to visualize in a 3D manner what really goes on. This is quite buggy, that's what I realized. So let's not focus on the animation just now. If we were able to successfully run the animation, then you'll be able to see this whole section going downwards when a force is applied. So what you expect to see in a qualitative manner will be shown in an exaggerated way. So that's what you'll see in an animation, but perhaps I need to add some solution fields before I run animation. I don't really know. I was able to obtain it before, but right. So let's leave our simulation at this point. If I run an animation successful later on, I will send a video recording to both batches, and you'll be able to figure out how to add the animation. But this animation isn't really important, since using these plots alone, we'll be able to figure out what goes on with regards to deformation and displacement and any internal stresses which occur inside. Now that's it with regards to the tutorial. What I wasn't able to show you was how to import a geometry, and that's kind of easy. You just click on add, click on the add sign next to the geometries tab, and drag and drop a SolidWorks file or whatever native CAD format you see from the list of these modeling software, or else you can use step files as well. Well, that's simply how you import a geometry, and after that, you move on to specifying the model parameters, the boundary conditions next. Pay close attention when specifying boundary conditions, and after that, you specify how the mesh uh, should be. Specify mesh requirements based on mm, specify mesh requirements if needed, and finally run the simulation. And after that, process the results, then go over the result plots carefully, and you will be able to obtain qualitative and quantitative results for the simulation. Well, that's it with regards to this simulation. I have nothing else to show you other than my failed attempt at running an animation. I'll figure out how to do this later on and send a video to you. So now's the time for you to ask questions, and I'm open to a Q&A session. I hope at least one is not sleeping and has been awake throughout the whole session. The issue, or the only issue I have seen with SimScale is that due to its low user base and since it's relatively new, there aren't that much YouTube videos out there which guide you through certain tutorials. You take SolidWorks, for example, then you will be able to find a large amount of such tutorials, but that really isn't the case for SimScale. You are stuck with figuring out things on your own by referring to the documentation and the limited amount of tutorials provided by the software itself. But at the end of the day, unlike 3D modeling, FEA and CFDs, some skill that you master through reading scientific papers and textbooks mostly, and by gaining experience based on studying what other people have done and what has worked for them in particular cases. Okay, then at least not a single question.
Sir,
Yeah, please.
can we use assembly drawing import in Simscale to use analyze the
Yes.
analysis?
Yeah, we can import assembly drawings. Not assembly drawings, but we can import assembly files. And when we import assembly files, according to the documentation, SimScale will figure out the contacts and connectors on its own, and you won't have to specify what those are. Uh, and just like just like the simulation that we did today, after importing the CAD file or the step file for the assembly, if you figure out these two parameters, then you can move on with the other as if nothing happened. But the case is, as I described earlier on, so I think I forgot to go over through this slide, but SimScale is not really a software you use for modeling systems. You leave that to Simscape and Simulink. We use SimScale to really model the effects on a single body and study whether a single part fails or not. I think you are referring to a robot arm. Am I correct?
Yes, sir.
Yes. In such cases, so what software you would need would depend on your objective and what you need to study. If you import your robot arm into SimScale, then of course by giving some boundary conditions, you will be able to run some simulation and obtain some results and perhaps an animation too. But we'd have to ask us whether that is really important, is necessary. Because in your case, you can do the same. You can import your assembly into Simscape, and the modeling or the studies that you can run on the whole system in Simscape would yield good results, but not. So let me rephrase that. The studies that you can run in Simscape for your particular application would be more beneficial and more advantageous, and most importantly, they will have meaning. You'll be able to figure out what your payload is and what your maximum accelerations would be if you run your simulation on Simscape. But if you, I don't think you would be able to run any meaningful simulation on Simscale. You can import part by part and check whether the parts fail or not and whether the parts undergo any deformation. But other than that, I don't think in your case you would gain anything beneficial uh, from importing it into SimScale and running simulations. But as I
Yes.
mentioned, yes. So did it answer your question, or do you have any more subsequent questions to ask? So that's why I included these slides. It's really important to know which software to use for which application. Otherwise, you just end up wasting a large amount of time. And as I mentioned before, by specifying some boundary conditions, you can model something and obtain something as a result. To have colors and whatnot, and it will be a nice thing that you can show to others, but won't really have any meaning. You can obtain some animation too if this is animation is successful, but you what you would really see is a small animation which takes place before you the small animation with regards to any deformation or small invisible deformation which is undergone, not the real kinematic related motions that you want to see. So that was a good question. And that question was really with regards to the applicability of SimScale to his particular application. If any more have questions like that or questions from uh, the kinds of applications, I'm open to them since we have some time left. So are rest of you sleeping at the moment? That's fine. So you can, since this is being recorded, you can view it at your leisure. And in addition to what I have given you in this video, I suggest you go over to the Simscale YouTube pages, YouTube channel as well, and see what they have uploaded. But you will see that most of the videos that they have provided are for the CFD domain, which is extremely difficult compared to static structural analysis. And I don't think any of you will come across the need to do CFD. Perhaps the automotive guys will, since CFD is kind of done when studying new kinds of engines and so on. But then again, if you don't have any questions, I can finish this session and people are already leaving. So I'll give you 1 more minute to ask any questions if you have any. Doesn't necessarily need to be in English. You can ask it in your native language as well. What I have noticed is you will try these at home and then you will run into questions and ask them. That's fine as well. It has worked for MathWorks. So I'll assume it will be that you will run simulations at your leisure, run into issues, and then you'll ask questions. So when you run into such questions, the fourth years have my number. I don't know whether the third years do. So please contact me and I'll raise your questions. Well, that being said, I'll stop today's session and thank you for participating, even though it was after hours. So you can leave now. And if no, two people will have to remain, two third years will have to remain since have a small project to discuss. And if any of the others don't leave, I just assume that they have been sleeping this whole time. Okay. So, Harsha, are you from the third year project group? All right. Okay, Harsha, so we'll switch over to Sinhala to discuss our project. But I can't hear you yet for some reason. I have my volume at the maximum and I can't hear you. And your mic icon is not moving, so I think perhaps your mic is disconnected or something else. And I'll have to stop recording us.